So our second speaker this morning is Will Keane from ARM. He's a senior engineer in the CPU group and has been there for nearly 4 years. His main area of interest is formal verification, and he has been responsible for deploying formal verification methods of several ARM CPUs. And the title of Will's talk is Formal Verification by the Book, ISA Formal.
Thank you very much, Mike. Is this on? Can you hear me? Okay, great. So yeah, my name's Will Keane. I'm going to be talking to you about ISA Formal, which is an in-house verification methodology developed by ARM within the CPU group. I've been involved since the creation of the methodology, and in the past couple of years, I've been responsible for its global rollout across all the projects within the group. So let me give you a quick kind of roadmap of where we're going to head with the presentation. To start off with, I'll illustrate the background problem behind why this is justified, why we need something like ISA Formal. I'll talk about why I call it verification by the book, what's behind that name, and what ISA Formal entails. I'll talk about the successes that we've had so far with the verification methodology, and then I'll talk a little bit at the end about what we hope to achieve in the future. So to get going, the problem, CPU verification is really hard. Our job is a difficult one. The CPU pipelines that we build at ARM, our designers are constantly coming up with new techniques to optimize performance. This includes all these kinds of things appearing behind me, sort of crazy design techniques to try and enhance the performance instructions per clock of our processors. And this is great. It ends up with ARM shipping best-in-class performance cores across the board. But while the designers are happy, this gives the verification guys a big headache, because an increase in the design complexity always gives you an increased likelihood of design errors and a greater number of pathological corner cases inside our designs. So let me illustrate this with a real-world example. So this is Cortex M7. This is the pipeline, the main execution pipeline for Cortex M7, one of our processors. As you can see, there's lots of functional units, and one of the key things with Cortex M7 that gives it excellent performance is its data forwarding paths, the ability to pass around speculative views of data inside the processor. So I'm going to illustrate for you all the data forwarding paths that exist within the core pipeline. So there you go, you can see them appearing behind me. And that is a lot. That is a lot of different forwarding paths, a lot of different possible interactions between instructions within the pipeline. And if you can imagine trying to verify this, you have to verify every possible sequence of instructions that can activate every possible sequence of functional units, forwarding to every other possible sequence of instructions, activating every sequence of functional units. So to do this exhaustively is extremely difficult. The state space explosion happens very, very early, very, very quick. And for a simulation verification methodology where you have to write your stimulus, you have to think of all the corner cases ahead of time. All the different instruction sequences that you need to hit, and this is very difficult. So aggressive data forwarding, it's great for performance. M7 has a great IPC, but it's a nightmare for those of us who have to verify these things. I'll give you a slightly scarier example. Our biggest core to date, Cortex M33 this is a kind of visual representation of the forwarding paths within that core. Looks a little bit like the London Tube map. That's just an artist's impression, but the serious point is that this is even harder. There's more speculative state flying around inside this thing. It executes instructions out of order, and so vastly more dependencies between instructions are factored in the final data forwarding network. And again, that just leads to far more corner cases, far more different possibilities of things going wrong inside the core. So the impact of all this on verification, it's needless for me to say that this makes verification harder. It's harder to think of all the different corner cases for your stimulus, and then it's very hard to stimulate them, and also it's hard to cover them as well. It's hard to demonstrate that you genuinely have covered all these different possibilities. It adds up to the increased likelihood of errata being bugs shipped in products to customers. These are really not an option for a company like ARM, where our partners ship billions of units of our processors, and it's very difficult often to patch those kind of problems in software. So this is just not an option for us. So we need to catch these things early. So at this point, we're at a formal verification conference. So you'll expect me to say that formal kind of rushes in and solves everything. The breadth-first search nature of bounded model checking will, of course, find the corner cases. You don't need to write your stimulus ahead of time. Of course, the tool will consider for you all these different possible horrible forwarding paths and speculative views of state within the processor. But the problem is that without the suitable properties as checkers for the tool to work with, it's more or less useless. You can't actually verify anything unless you have the checker. And this is where ISA Formal really comes in and comes into its own. So what is ISA Formal? What am I talking about when I say ISA Formal, and why do I use this tagline of verification by the book? Well, verification by the book, where the book is the ARM architecture reference manual, the ARM as it's referred to inside ARM. We do love a good acronym. So what is this book? It formally defines the precise semantics of the software-hardware contract. So if the software engineer writes an instruction sequence, he can expect it to behave exactly as the book says that it needs to behave. And the dream that we have in ARM is to robustly verify all our processes against the ARM architecture, particularly using formal methods. If we could exhaustively prove that the entire ARM architecture is adhered to by a single processor, then our verification work is done. We wouldn't need to do anything else. But the problem comes then, if you say, if we want to do this whole thing, that's nearly 6,000 pages. And the classic way of doing formal, where you read a spec and extract properties from the spec and then apply them to a design, that's fairly intractable with any number of engineers. The ARM, let me illustrate for you what the contents of the ARM is by area. This is a histogram of it. I don't expect you to read that, but I'm going to highlight some areas to you. So the area, if you like, represents number of pages. So that is the ArchEx instruction set, that glob there that I've highlighted. So that's our 64-bit instruction set. There's still 32-bit encodings, but that's a 64-bit architecture. That's the 32-bit architecture, the V7 legacy architecture. And that is a shared library of common pseudocode that is used by both of them. And between, if you add all that up, it's just over 50% of the spec, around sort of 2,900 pages, something like that. And this constitutes the ISA, the instruction set architecture, which is where ISA Formal focuses all of its efforts, just at verifying this instruction set architecture and the processor's adherence to it. So how does the architecture actually define instructions? Well, it views them very simply. Each instruction is simply a function that maps one state to another state. So, for example, if you start with state 0, instruction 0 would map that state onto state 1. And the programmer's model just consists of a piece of software, a program, which consists of a sequence of n instructions mapping the processor state between state 0 and state n+1. And we provide these instructions as means by which to do those mappings. And every instruction is specified by a piece of executable pseudocode. And when I say executable, I mean that our pseudocode is tightly defined as a language. It has a precise semantics, it has a type system, it's fully kind of interpretable and readable. So every instruction has a definition in the pseudocode to specify exactly what it must do. So as an example, an add instruction, so in the ARM mnemonic, that means add x1 and x2 together, the contents of those registers, and then store it in x0. So the below pseudocode could be an implementation of that. So if you think of the add instruction as a function that maps a state to another state, then the pseudocode could look like this. You simply say that the x0 field of state 1 takes the value of the x1 state field of state 0 added to the x2 field. So it's very straightforward. The architecture views all instructions in a kind of simplified way like this. They simply must perform particular pieces of behavior. However, the implementation of our architecture in our processes is much more exciting and not as straightforward as this. As you saw on M7's pipeline earlier, there are many speculative views of the architectural state flying around inside the processor at any particular given time. So the question that we need to ask before we can do any kind of architectural formal verification is whether we can actually extract the architectural state from a real pipeline. Now remember, let's use these definitions of state n being the state before an instruction n executes, instruction n being the opcode, and then state n+1 being the next state. So let's take the Cortex M7 core as an example. Here's the pipeline again. So what would we require for the architectural view of this core? So let's take the register file just as an example. That's just one part of the architecture, the kind of integer register file, general purpose registers. So what we don't need for the integer register file is anything inside the pipeline. We don't care about speculative execution. We don't care about the forwarded data values that are flying around inside the core. So we can completely ignore the pipeline. And we don't need to know what's going on. That's independent from what we're interested in. Because for the register file, the architecturally committed values live in the register file. And because this is an in-order processor, all writes occur here in the WR stage across all these functional units. And the architectural values are updated when an instruction reaches this WR stage. So all we need to reconstruct our architectural state is the instruction, which the opcode will be observed as it goes through the prefetch, fetch, etc. stages of the pipeline and reaches the WR stage. And then as that instruction reaches the WR stage, we need a snapshot of what's in the register file at that time, the observed register values, that gives you the state before the instruction executes, and then the observed register writes happening from the WR stage. That gives you the update to the state to give you state n+1. Now, again, as I said previously, all of this is moot unless we have some logic to give us the expected values and to do the checking against. And that's really what the other half of what ISA Formal provides. When we began with some handwritten checks, but we got smarter. There's a tool in ARM called Architecture Explorer, which is often shortened to ArchEx or ArchEx. The pronunciation guide is not clear there on which way it should be. It's an in-house tool developed by Dr. Alistair Reed, who's a chap from our research department. Originally, it was spec'd up as an interpreter to execute the ARM pseudocode in an interactive environment so that a user could examine the behavior of a different architectural instructions or function calls to see what effect they would have on the architecture. We asked him if he could go away and make it output some system Verilog for us. He came back in a couple of weeks with a prototype, and it's been working more or less ever since with plenty of enhancements. So what it does is it takes the pseudocode and translates it to system Verilog. So there's a diagram of the flow. You take the ARM, the Verilog, the pseudocode defined in there. You put it through the Architecture Explorer flow, and it outputs an auto-generated system Verilog ARM architecture, and which takes in a state and an instruction, and then maps it to a next state. We tend to call the state before the pre-state and the state after the post-state. It's important to remember that this model has no flops in it. There are no registers whatsoever. It's just a combinational model that takes in a state and an instruction and outputs another state, so no persistent state whatsoever. So how do we actually apply this to a real processor? Well, you start off with the DUT, the CPU RTL, the system Verilog, and you have the ArchEx VIP. You have the auto-generated ARM architecture, and somehow we need to use this to do verification. We need to extract, as we discussed earlier, the architectural state from the DUT, and for that we need a bridge component that kind of hooks into the signals inside the RTL and extracts that architectural state. So there is the pre-state being extracted by the bridge component, and that is fed to the VIP. You also feed it the instruction and kind of enable signal to tell it this instruction is executing now and it's valid to do checks. And then what you do is you take the two outputs and compare them, thusly, through a set of properties. And the properties are effectively comparing the post state, which is the state observed from the DUT, against the arch state, which is the expected state, which is output by the auto-generated ARM architecture. And properties exist per instruction, and they exist across all different areas of architectural behavior, such as the register file or the program counter, memory behavior, system registers, etc. The main details really that I've glossed over in this presentation is exactly how to do this bridge for different processor microarchitectures. It can be very, very difficult. The microarchitecture deliberately kind of obscures the architecture for performance purposes. That's what we do really in our pipelines. And there's all sorts of things which make that difficult. But what we found is that there's often low-hanging fruit. The register file, in particular, in an in-order core, constitutes low-hanging fruit. It's actually slightly more difficult even for M7 that I've illustrated an example of, because it's a superscalar processor. It has dual issue, so extracting those register writes is slightly more difficult than I explained. But everything is possible with a little bit of hard work, a bit of elbow grease, and some tracking logic. That's what we've discovered. And we've discovered that it scales to different, completely different architecture specs. The A, R, and M class specs that we have. You notice that spells something again. And it also scales to different microarchitectures, of course. So really small M class cores all the way up to colossal out of order A class cores. So it does work. It is possible. So I've talked about how we do it. Let me talk now about the strengths of it, why it works, what's good about it. So for starters, the very basics is that we check the architectural functionality of each instruction. So when you're building a processor, your designer might come to you and say, right, I've built a basic pipeline and ads should work now, I reckon. So you can take the design and you can check whether an ad works. So basic bring up kind of tasks. So this could be long before the simulation test bench with its complete model is anywhere close to being ready. You can bring up your processor on an architectural level. And then once you've done your add instruction, you can move on to more complicated instructions like branches or memory instructions or supervisor calls, etc., etc. And particularly when there's a brand new architecture, such as when we brought up the V8M architecture on Cortex M33, that was our first implementation of that. It finds corners that you don't expect because you don't understand the architecture yet. So it's a brand new architecture. It can be very, very difficult to understand some of the finer points. And so just bringing up those new architectural features is a key win. And so by implication of checking the architecture, you also end up checking the microarchitectural functionality. And let me illustrate this with an example from what we've discussed already, the integer arithmetic with the data forwarding paths. So in the CPU pipeline, very rarely will an instruction actually ever read the register values from the register file and then write back the result neatly. It will usually be based on some kind of speculative state, either through data forwarding or through something else. So the CPU pipeline does it based on this speculative view of the architecture. In ISA Formal, this is done based on the register file, based on the committed architectural state. And the key thing here is that if the final register write mismatches inside the DUT because of bad forwarding, we get a counterexample. And that covers any cases where the forwarding has gone wrong to the final instruction in the sequence. So when we're checking an add instruction, we're not just checking the add, we're checking all instructions executing before the add, forwarding into the add, and creating a different result between the speculative architectural state and the committed architectural state. And it works the same way for all architectural state, not just the register file. So branch prediction, conditional execution, etc., anything works this way, that if the speculative view goes wrong inside the processor, you get a counterexample, you find the bug. Continuing, why else it works? The architectural model is extremely valuable. For starters, it's auto-generated, so you miss out that potential step for misreading the spec and having properties extracted from a specification which are not true, which are a misinterpretation, and then proving them against the design. It's stateless, which is really good for the formal tool. It means it scales well. It means the checks are done in one cycle. It's reusable. Very many projects within ARM, I'll illustrate how many later, use the same VIP generation. We can also generate some coverage metrics to sign off against as well in terms of what instructions we've checked. And formal, of course, is the big win. The fact we use formal methods over and above simulation for this particular application. The corner cases that it finds are the real key thing here. They're using the breadth-first bounded model checking. We kind of leverage that power of formal tools to be able to to do that, to poke into all the nasty corner cases, and we end up finding lots of bugs that dynamic test benches simply can't find. They're just out of scope of the stimulus. Incremental checks. We can begin applying checks long before other areas of functionality are ready, so we can start with an add instruction. We don't have to have a full model, a full state tracking model, like a test bench does, before we can start checking meaningful stuff. And of course, when you check an add as well, you're checking, as I said before, every possible instruction sequence leading up to the add, not just the add itself. And that also leads on to the assume guarantee strength of formal, where you might be thinking so far, well, when you're checking an instruction, you've assumed that all the instructions executing before it have left behind a correct committed architectural state. And you'd be right, that is exactly what we're doing. But that's fine to do in formal, because you'll go back and you'll check those other instructions later with the properties that verified them. So this is a neat way to chop up the architecture and verify each bit in isolation. So I've told you about how it works, at least from a theoretical standpoint, but what's it actually achieved? So let me go through that. The CPUs we've deployed it on, this is a list of all of those that's appearing. All of these, as well, I should mention, are CPUs that have been developed in our Cambridge design office, in the CPU Cambridge office. This is a Cambridge kind of born and bred methodology, but we are also rolling out globally to our other sites. Sophia in France just completed a trial run of this on the recently released Cortex M33 processor, and there are to-be-announced processors in development in our other sites, which are also deploying the ISA Formal methodology. So you can see it scales across a vast range of architectural classes and performance classes. As a case study, let's take Cortex M33, as I've mentioned before. It was the first processor to implement V8M, a new architecture and a new microarchitecture to do that. And the key new architectural selling point was is the Trust Zone M, the M-class security extensions that live in the hardware rather than the software. And so that's vital to verify from an architectural perspective. The effort on the project was one graduate engineer who started mid-project cycle. And really, we had a lot of success with this. We found many unique bugs, not reproduced anywhere else, not found anywhere else. We were very compute efficient, which I'll try and demonstrate, and resource efficient in terms of the number of engineers and experience required to find the issues. Let me first of all show you the bug curves. These are bugs, unique issues found only by ISA Formal and accepted as real issues and fixed. So over a kind of nearly 2-year period, we found and fixed over 120 issues. And as you can see, it functions very nicely as a kind of project manager's dream S-curve, very nice. It jumps up in the middle of the project development and then kind of flattens out very nicely towards the releases to prevent any post-release bugs. So we're very pleased with how that went. Bugs per week per methodology. So this graph is going to show you formal, vanilla formal, ISA Formal, and simulation. ISA Formal is the light blue on top. The colors are very horrible on that projector, do apologize for that. The purple-ish is vanilla formal, and then the big chunk on each one, the red, is simulation. You might be looking at this and thinking, well, simulation clearly has the lion's share here. There's clearly a whole bunch more simulation bugs. And that's true. But if I plot you another graph of CPU hours spent per bug, per methodology, it tells a different story. So it shows you that Formal was actually more efficient in terms of the number of cluster hours required to find each bug. Fortunately, with this graph, we've lumped formal verification together, so ISA Formal and kind of more vanilla kind of formal methods. So generally speaking, far more resource efficient and compute efficient in terms of the number of bugs it found. Of course, I'm not saying we shouldn't do simulation. I'm just saying that as a complementary verification methodology, we can add a huge amount of value with not too much extra investment. As a further thought, the quality of bugs is really important. So it's not just quantity, it's the ones that are missed by the other verification methodologies that are never found by a simulation test bench or by vanilla formal methods, by the kind of standard formal flows that we employ. And the end-to-end nature of the checks has meant that lots of issues that you just wouldn't expect to come out of certain checks have been found along the way. The return on investment has been very high. Generally speaking, across all the projects, we've had less experienced engineers do the ISA Formal work, who then become kind of experts in their own right. They become formal experts as well as becoming kind of ISA formal experts. And what we found is that with these guys in the teams, they've really helped the simulation guys because they can cross-communicate on issues where one methodology found something that the other thinks it ought to have found, and vice versa, and help each other improve their verification. And as I've said before, it's highly portable. We've ended up covering all the architecture profiles from M4, which is a very small processor, all the way up to A75, which is massive. And so very quickly, just to close, I think I've got a few minutes, where are we going next? Got a couple of slides here. So to start off with, we want to share our successes across the board inside the company. We want to deploy to all the ARM CPU projects, which is something that's going on as we speak. All the projects are taking this methodology on and applying it. We want to democratize the experience. At the moment, it does feel a bit like there are these experts who apply it, and then they train and mentor others. What we want to have by the end of this is really a flow which can be just used as a push-button flow, even by designers, just to go off and say, right, verify my add instruction, make sure it works properly. And we want to enable easier deployment on the next round of projects so that we can just get this up and running quicker and finding bugs quicker. And also we want to consolidate the collateral, the VIP, and the generation processes for that. The tools maintained already by the TSG Technology Services Group formal team run by Daryl Stewart, who many of you will know. This enables easier deployment on each project and enables improvements being rolled out quicker across the board as well. In terms of future directions, the ISA, as I said before, is just over 50% of the spec. There's all the rest of the spec to go that we haven't done yet. So can we do something more? Can we turn this into architecture formal, not just ISA formal? Yes, I think we'd like to do that. We've identified a number of different areas of the architecture where we could apply a similar methodology with auto-generated VIP, and we've got efforts ongoing at the moment, sort of experimental efforts to get those initiatives going. And then we also want to encourage the use of this kind of thing within other groups at ARM. So it's not just the CPU group who ends up doing this. We've got the systems and software group guys. They have their AMBER specs, again, very tight architectural definitions, and our media processing group with their architecture as well. So we'd like to encourage this to happen across the company. So just as a summary slide, the verification by the book aspect, we automatically generate VIP from the architecture spec and apply it with formal methods to our cores. We find bugs. It's found bugs on all the applications before we've released the product, not the ones where we've applied it after we've released the product, fortunately. That would be embarrassing. The vast scope of possibility, we've just begun to tap into it. It could be really far-reaching in its impact. We're really excited about where we can go with this idea of architecture formal. So hopefully I've got a few minutes now for questions.
Thank you. Let's quickly go to Roger.
Roger Shepherd, Chipless. It seems, my understanding of what you said about the verification is that you're basically relying on the architectural state at the end of an instruction. In an implementation where you fuse instructions, between the two instructions you fuse, there is no need for there ever to be an architectural representation. Mm-hmm. So how do you deal with that? And guessing it might be in the way that you fake up an architectural state for that. Does that not put a lot of dependency on the assumptions about that intermediate architectural state?
Yeah, it's a very good question. So yes, you can split the problem up, kind of standard formal assume guarantee kind of method. As you say, you can fake out the intermediate state between two instructions with a kind of handwritten piece of prediction logic. And then you can have a different configuration where you forcibly turn off the processor's ability to fuse that instruction. And then you verify that your handwritten model of the intermediate state between those two instructions was in fact correct. And then that gives you a tight solution. Does that make sense?
You do that formally. You show that your mechanism for faking up the state is formally correct.
Yes. Yes.
Okay. I'll move to Ashley. Just one online. Just says, will this be made available to your architecture partners?
I can't comment on that personally. You have to engage with our product marketing groups, but that's not something I can comment on.
Hi, Ashish from OneSpin Solutions. Were there any bugs that were missed by this work and were found later in the design verification cycle?
Yes, this has missed a couple of bugs. Where we found bugs that this has missed, we've done a full investigation to understand why. There have been a couple of different reasons for that. One of them is the maturity of the Architecture Explorer tool, not quite generating 100% accurate to the spec VIP, but we've done a lot of work in terms of debugging that and correlating that against other verification methodologies to try and plug all the holes. A couple of other ones have been to do with the environment in which it's been deployed in, so a kind of standard formal verification environment problems like over constraints and things like that. But yes, we have missed bugs with it, but we've understood in every case where we've missed them.
Over here, Will. So we've still got over 70 people online. There's lots of questions coming in, so I'll pick a couple. Is this foolproof or bounded proofs? I think I know the answer, but
no. So we don't expect full proofs. We've achieved some full proofs on the smaller cores. We don't expect to yield proofs with this verification methodology. It's more about bug hunting. We tend to run it with engines that are more suited to finding traces rather than finding proofs. And we have various techniques and tricks to push that bug hunting effort further as well.
Okay, so it's more just a bug hunting. I'll just call one more out. Since it is checking for all reachable states every cycle, the property suite could potentially be huge. Is that a correct observation?
Yeah, it's colossal. Yeah, okay. One of the main problems with it is that it's difficult to scale the number of properties that we want to run against the compute resource that we have available to us, particularly when the design is changing all the time. So yeah, one of the big challenges is how to chop the properties up. We've done some effort into how to group them into similar areas of behavior. So instead of grouping each individual bit in a register, it's checking them individually. You can group them together into one check, that kind of thing, but for the system registers. But yeah, as the architecture is huge, the number of checks is huge.
I'm going to take one final question.
Hi, it's Karthik from Huawei Technologies. A couple of questions. You didn't talk about any additional constraints that you've added, so you completely left it out of the slides. Are there any constraints?
No, you should be able to run this unconstrained, well, with the same level of constraints as you would apply to your normal formal core verification efforts. So we tend to run this just at a core level, so you're using the standard approach of making assumptions based on properties that you're going to prove elsewhere about interfaces off into the system. So for example, we wouldn't include the full memory system in the bench that we use to apply this.
Okay. Another question, how do you deal with external events, things like intros or SRs?
Good question. We do actually deal with them. As part of the architecture, we can deal with them. It does depend on how the microarchitecture handles them. There's various prioritization trees, which in the architecture are implementation defined. Therefore, a processor is allowed to do whatever it wants with these different interrupts that come in. There are configurability options for the model that you generate. So you can tell the model that you generate in advance, I'm running on a processor that prioritizes things A, B, C. The other one I'm running B, C, A, or whatever.
So the ARC model has some of the def. Okay. Final question. You're basically running bounded model checks. Do you run to a particular depth based on the course pipeline depth?
Yep. So of course we have to use all the standards kind of coverage thinking. So for example, verifying to a depth where you're satisfied that all your microarchitectural interesting events can be observed and can be observed together. So for example, the longest integer divide happening could be recirculated for many, many cycles happening at the same time as the longest interrupt handling mechanism, something like that. So you come up with those covers for the microarchitecture and ensure that you've run all your properties to at least the same depth. perhaps non-exhaustively, perhaps not doing from depth BMC, but doing BMC at least at the depth of all those interesting pieces of microarchitectural coverage.
Thank you. I've got the conch shell back now, so I'm going to wrap it up there. So thank you very much.
Great, thank you.